Hello and welcome to Learn ADS in 5 minutes. This is tutorial 43 on multi-layer RF layout design using Keysight ADS. In this tutorial, we will talk about footprint modeling, technology referencing, RF board routing, layout versus a schematic, and DRC checking for our multi-layer RF layout designs. This video is in continuation to the previous two tutorials I posted on my YouTube channel. So please go ahead and watch tutorial 41 and 42 before you continue with this video. These three videos put together will give you a very solid foundation to get started with multi-layer RF board laminate module packages or LTCC design very easily. Before we start, subscribe to my channel. Once you subscribe, click on the bell icon to make sure all the notifications are enabled. And don't forget to hit the like button after you watch the tutorial and click on share icon to share it with your friends and colleagues who may be interested in watching similar content. All right, let's get started. This will be slightly longer tutorial as we have a lot of important things to talk about. So hopefully you will stay tuned till the end of this video and grab everything which I'm going to talk about in this video. All right, so we will start from the same multi-layer example we were working on in the previous two videos, and we already have our multi-layer, 6-layer kind of stack up already defined. Now, because we are going to do footprint modeling and also we are going to create a kind of component library so that we can use it for our circuit design or board design application, I will go ahead and do a little bit of modification to this stack up. For example, here I will go ahead and map a new layer, and let's call this layer as solder mask. And in terms of process role, I can go ahead and choose the process role as solder mask. Once we done, you can see there's a solder mask at the top. Similarly, I'm going to go ahead and I map another layer, and in this layer, I'm call it comp body top because we are going to have top and bottom. And in terms of process role, I'm going to define the process role as component body. Similarly, on the bottom side, I'm going to add a new layer and I will call this solder mask underscore BT, which means bottom in our case. And again, let's go ahead and pick solder mask definition. Now notice the solder mask definition I could have avoided during the technology creation if I would have selected solder mask definition in the stack up setting. All right, so let's go ahead and map another layer for the bottom comp body, and let's call it BT. And again, in a process role, I'm going to define it as component body. Now, these process rules are kind of very important because if you use the same substrate for your EM simulation, all these layers will be ignored and the EM simulator will mainly focus on your metal layers. So having the right process rule is kind of pretty important to make sure no unnecessary items get analyzed. Okay, so here you can see these interface is looking up, so I can change it to below interface for both of these so that when I look in the 3D profile, the views come out properly. The height of component body, just for the 3D viewing purpose, I'm going to define as 10 and 10 mil. And for solder mask, for top and bottom, I'm going to define 1 mil as the thickness. All right. And this is again just for the 3D view, nothing very special. Now, once we have this stack up, we can go ahead and create our first layout. And let's start creating our first footprint. And let's call this footprint as chip 0201. And because I'm going to do it first for the top side, I will make it underscore top. Now once I have the layout, I can now start doing my footprint modeling. And also there are plenty of references online where you can get all the recommended pad sizes for your PCB application. Or if you have your own size chart, you can go ahead with respect to that. Now here I can see I want to make it for 0201 size. So here are the dimensions, and for me only ABC is main important. So A minimum and maximum is mentioned here. So we'll choose something in between, maybe 15 mil. And for the B dimension, which is basically the pad, kind of length, I'm going to select 10 mil. So 15 by 10 mil is what I'm going to use for my, footprint. All right, so selecting the con, which is the top layer, we can quickly create a rectangle, and using the coordinate entry here, I can see the X and Y coordinate, and according to that, I can pick my size as 15 by 10. Now, if you want to do more coordinate, oriented entry, you can always go to insert coordinate entry, enter your X and Y coordinates, and start creating your polygon. Right, so the separation between the pads in as recommended here, C, is between 8 mil to 14 mil. I'm going to choose 10 mil, somewhere in between again. So this coordinate, as you can see, X equal to 10. So now I can go to X20 and again do the same 10, 15. So very, very simple. So I have two SMT pads on the con layer. Similarly, if I want to create a solder mask, I can select solder mask and then just create a rectangle which are kind of overlapping to these conductors. Again, you can go ahead and add solder paste or whatever definition you require. All right, so now let's make a component body outline. So here is my component body top, because I'm preparing this footprint for the top side. So let's make it that layer as activated. And now I can just draw a simple rectangle somewhere inside this, or maybe encircling this pad as per you need. But now you can see my grid snap is switched on and it is moving in a 5 mil, kind of step. And we can simply set that grid size by going to option preferences, or if you have enabled this layout command line editor, I could just click on this icon here and change the grid size to be 1 mil. Now here, because I enabled the grid snap here, now my mouse will move in a 1 mil, kind of step. And again, you can set it as per your requirement. Right, so this one is going to represent my, component body outline. So I'll go ahead and insert a rectangle there. Now, once I have my footprint basic shape, we need to connect the pins, because ultimately this footprint will be used by a 2-pin component such as inductor, capacitor, and resistor. Now create a pin, the best way to do that, so that, to make sure that your footprint doesn't give you LVS error at the at the end when you do your design qualification. The good idea is to make this entire pad as a location for port connectivity or the trace connectivity. And the simple way to do that is by simply right clicking pin and make it one pin from selection. And now you can see it places a pin, an entire rectangle as selected as the location for connectivity, or as the pin area. And if I double click on this pin, you can also see that here in terms of shape is rectangle 10 by 15 mil. Similarly, for this side of the conductor or pad, we right click, pin, create one pin from selection. And for some reason, if you have to rotate it, just press Ctrl R and you are back to the shape. Right, so as simple as that. So this way you can go ahead and create as complex, footprint as you want. Right, so this was for simple chip, size of 0201. Similarly, we can go ahead and create, footprint for 0402, 0603, 0805, etc. Now, just for the variety's sake, I'm going to show another footprint, and let's, use a QFP quad flat, pack kind of thing. And let me create QFP and call this a sample. Now for QFP kind of structures, you need a kind of array and on all four sides to create a footprint. So here, using the same knowledge like we did earlier, I'm going to create a rectangle. And again, this rectangle, I'm going to create something like, 10 by 5, for example. I find it easier to work in a grid, but then again, as I said, if you don't find it convenient, always use the coordinate entry. Now, once I have one pad defined, I could select that pad, go to copy paste, step and repeat. Now with the step and repeat, I can define X or Y spacing, number of rows and columns as we want to create a pattern. So in this case, I'm going to create number of rows and I need 5 rows on a side because I want to create a 20 pin QFP, kind of footprint. So I can place the one array component here. And now I can just see Control C, Control V, and Control R to rotate. And I can go ahead and place these, pads as per my, QFP dimension. Now here again, I'm doing something pretty rough just to show you the concept. In case you have more, measured data available with a proper dimension, go ahead and use that to create a proper footprint. Now this pretty much looks like a 20 pin QFP. And now again, because I'm doing it for the top, I can go to component body top, and I can just create a component body, kind of outline. So I can either use a simple, rectangle like this, for example, or in case I need some identification like corners or anything, so I can go ahead and use, polygon here. And for example, in polygon, when I reach up to this point, I can go ahead and give it like identification, kind of notch. So depend upon what you want to do. So now once you have QFP, how am I going to, put the pins on this footprint? Now, again, as I said, we can right click on each pad, you go to pin and create one pin from selection, but then you need to do that 20 times and not very convenient sometimes. There's alternate way. Now, other way to get this option is to go to EM menu in the tools, and you have the same option here. And you can see I have created a hotkey for that, kind of command, so that using keyboard, I can do things very easily. Now, in your case, this hotkey will not be there. So the way to make hotkey is go to tools, hotkey, and toolbar configuration. Under hotkey, just go to the menu. So my option for the command was under EM tools, and I had this command. So once you select that command, you can assign any hotkey, and you can see I have assigned Alt Q already. So that means I can just select this pad, press Alt Q, and I have this pin here. So again, depending upon your preference, you can assign whatever hotkey. And here, sometime, you need a good starting point, and having little bit of ADS symbol generator knowledge will come in very handy, because ultimately we will have a schematic symbol which will represent this in a schematic design. And if I am going to use the default symbol generator in ADS, that's how it starts, nomenclature. It always has pin 1 here, and then it goes anti-clockwise. So here, just to help myself, I'm using the similar configuration. So if you don't select the pad and you press N2, it says it is already having a pin. So not a problem. We can always click correctly. And here, let's keep on doing that very, very quickly. Now there is one option where I can place multiple pin at the same time. That means in one command, I can place, all the pins in this symbol. However, there I cannot control in the, order in which ADS will end up generating, the pin numbers. And if I need more deterministic order, how I want to, put the pin numbers, then I go this, by this method of one by one. All right. So now I have all 20 pins placed already in my symbol, in the footprint. So everything is ready. Now to create an equivalent schematic out of this, because we will need that schematic and symbol for schematic design, I could simply go ahead to schematic menu and click on generate update schematic. And now these QFP, kind of devices effectively, so let me close this layout, has no schematic relevance as such, because in a schematic, you will only have these 20 pins representing that component. We want to use this QFP only for the layout assembly, kind of job. So it's absolutely fine if a schematic looks rubbish, and you can, kind of reorient all the ports the way you want, because this doesn't have any significance. All right, so we have a dummy schematic with our design and the layout, and we also have a chip, kind of layout. Now, so these are two different things, and soon you will realize why I am doing that. Now, if I have to create a component, and in that component, I need to assign this, kind of footprint. So there are a couple of ways. The one way is you have a schematic, and you have the symbol right there. So this is like a self-containing cell or component which can be used in your board design or any module design you're doing. The other way is let me show you. So let's create a new schematic and let's call this component as sample cap 0201. Now I could separate out the footprint from the component. The advantage of that approach is that you have this footprint which is representing a component size of 0201. Now the same footprint could be used by capacitor, resistor, inductor. I don't need to do this footprint modeling 3 times. I can do just one layout and then I can use that layout in all the components where I need. Now let's see how can we create this kind of parametric component here. So for example, I'm going to take a capacitor, and now for this capacitor, I will need to associate that footprint. So let's see all the steps. First, because this model will be used as a sub-circuit, so we connect 2 pins. And remember, these 2 pins have a significant meaning. The one pin will be at the origin. So whenever you place this component, in any schematic, you will always have your contact point here, and this is the origin point, right? This is how the symbol will rotate or move or shift whenever you try to drag and move it. All right, so we have the component. Now to make it parametric, I don't need to hard code a value. I can just define some variable C, which effectively I would be able to specify later. And in order to pass the value to C, like I showed in one of the earlier video, I can go to File, Design Parameter, and under Cell Parameters, I can define the parameter called C, and this should be the same name which I specified here. Now, in terms of value type is a real value, and I'm going to define 10 picofarad as a default value. Whenever I place that onto a schematic design, this is the value this component will get initiated. The parameter unit type obviously is capacitance because I'm going to build a capacitor, and I've selected all these options to be activated. Now, when we click OK, this parameter get attached to this particular design. Similarly, I can have another variable or parameter attribute part number, and that part number is going to be a string, and now I can define it as a string here. Now, if you have any specific part number in your company or you want to identify this component by specific part number, you can type in. Here in this case, I'm just going to keep it as TBD. Right, put that in double quotes, and parameter unit is going to be string. There is no unit as such, and again this is optional. And now I can define anything which I want user to see if he double clicks on this component, part number of capacitor. All right, and but this is just a part number, so it has no very no impact on our simulation. So I don't want to netlist this. I don't want to make it editable either for user. Right, so let's go ahead and add. So I have 2 attributes now attached to this design. Now in the general cell definition, I can define how the component starts naming itself, right? So here you can see it's called C1, and if I place another component called C2, C3, and so on. And if you want, you can use the same name here. Let's say C. So now it will be called C1, C2. Or if you want to call it MyCap, then it will be named as MyCap1, MyCap2, MyCap3. I mean, choice is yours. So to keep it simple, let's refer this as C. Now, once we save and click OK, now I have this capacitor component ready. Now, in order to use this component into the rest of the designs we have, in our actual project work, I need to have a symbol. So let's go ahead and create a symbol. Right click new, and let's pick symbol. And now symbol editor opens up. So you could use all these options here to create your own customized symbol, and you can choose the print orientation as you may want to keep it. But in this case, I can go to copy modify, and now you have all the ADS, default symbols for different kind of components. So I'm going to scroll to the lump component library, and I'm going to pick this capacitor symbol because my component is also capacitor. And if you want to do any addition, subtraction to this model, you could do it. You can put your name or put some company identifier, things like that. But in this case, I'm not doing anything. So it's just a plain capacitor symbol. And now you can see you also have a symbol view. Finally, you would like to have a footprint to this capacitor. So for that, I'm going to create a layout. And in this layout, design here, like we did for QFP case, I could have a footprint right created here. Because otherwise, if I already know this capacitor size is going to be 0201, I already have a footprint file here. So in that case, I don't need to draw anything here. I can go to File, Customize P cell, and instead of using this layout as a layout view, I'm going to use referenced information here. Now I can reference any other design as a footprint or a layout view of this cell. So here I'm going to simply refer it to CHP 0201 underscore top. That's it. So now once I click OK, your layout will not have any view, but whenever you place this component and create a layout out of this layout will get replaced by this footprint, and I will show you very quickly how. Now before we go ahead, let's create a symbol for this QFP as well. So right click, new symbol for QFP, and again here I'm going to use a default quad symbol, and you can see how ADS nomenclates the port order, and this is exactly what I used in my footprint generation. And in here, you can see the origin point is around pin number 1, and that's how your schematic symbol will represent. Now here I am making one kind of mistake knowingly, and I will explain you what is that mistake and how does it affect, and then we will correct that mistake. Anyway, so this was the typical flow. Now let's test whether the layout is getting generated properly or not. Let's create a schematic, and let's place this capacitor here, like I just drag and drop. And similarly, let's place a QFN here. Like now, just for variety's sake, let's add one more capacitor here. All right, now I'm going to connect this capacitor to this pin and this capacitor, let's say, to this pin now. Right now, in order to generate this layout from this schematic, there are a couple of ways you could do, or rather 3 ways you could do. So one of the easiest way with a lot of RF microwave, circuit designer use, you go to layout, click on generate update layout. If all your components have footprint already assigned, this technique works straight away. So if I click OK, and now you can see you have a capacitors and you have a QFP footprint. And with this, rubber band line, you can see the connectivity information. And now you should be able to route, the path or the trace between these nodes. All right, so that was way number 1. The second way is, so let me just put it because I'm using a small laptop screen. So let's try to make our schematic little smaller. Now the other option is right there, place components from a schematic to layout. Now under this option, you could decide which components to place, where to place, and things like that. So now you can see with that option, a layout window opens up. All components get highlighted, which are currently not in layout. And now if I click on this capacitor, now you can notice I have a ghost image of this capacitor moving with my cursor here. However, notice the crosshair of this cursor, it at the lower corner of the pad. It's not at the pin location. So if you're trying to connect or trying to align this component at certain XY point, it's kind of very difficult here because you're looking at the lower crossing point of the pad. Anyway, let me place it. So I was referring to this point. Ideally, I may have wanted to be having that control right at this pin so that your connectivity job is easier to manage. But anyway, so I place one capacitor. You can see now it's cleared from here. I click on another capacitor. I can place it any location I want. And now let's click on this QFP. And now notice where is my mouse and where is component. Look at the crosshair at the mouse and look at the component where it is. You can see there is an offset between my mouse and the component, making my job much more difficult to place it at the desired location, right? Well, now, why this is happening, and this is what I said, I'm making a mistake deliberately to show you that if you don't take care of that, this is what will happen. So let me delete, that component. Let's correct the problem first. Now that problem was that when you created the footprint, you can see the origin, this crosshair. Let me make this layout a little bigger. Notice this crosshair is crossing at that point, and that's the origin point here. Okay, so during component creation, if you place the origin, you can do that by simply clicking on this icon and clicking, and now you can see the crosshair point, origin point has shifted to this node. So whether you want to keep it on pin, some people want to keep it at the center of the component, it's your choice. So I just prefer to keep it at the pin location here. Now I can save it. Now in case you don't have this layout command line editor enabled, the same command you can go from edit, modify, and you have this option here called set origin. So first footprint got placed at the right origin point. Similarly in QFP sample, if you notice your origin is here and the component is here, and that is why you are having that offset. So again, I'm going to place my origin, let's say referring to the first pin location, and now we have the origin here. Let's go back into the layout mode here, and let's say place component from schematic to layout. Now notice what happened to my capacitor. My mouse is right at the pin location, so I can place this component in an easier manner. Let's place the second capacitor as well. Now notice QFP, my mouse crossing point is right at that pin 1, right? So now we place that pin, and if you have to route, we can easily use the knowledge we have gained till now, of trace and editing. And now I can insert the trace at the desired location, and I can make my connection. Now notice here we have the avoid obstacle option on, and this is why it is not allowing you to go inside. And right now when I'm routing and connecting to these components, this option is not necessary. So let's uncheck that, and now I would be able to go inside, right? So let's route both of these traces. Now again, another thing, to connect, you don't need to really touch this component here, because if you are only touching this particular piece, then also the connectivity is done. Remember, because this entire pad was defined as a connection pin, so as long as you touch that component, that should be fine, and you will plus LVS or DRC checks, there's no problem. All right, so once we routed this board, but here it's only doing on the top side. In multi-layer board, I might want to place components at the bottom side as well. So how do we handle that? So let's save this layout for the time being. Now for bottom side, again, there are a couple of things needs to be done. First, I need to have a footprint, which is defining the bottom side placement, kind of concept. So here I can just right click, copy cell, and now I can copy it and name it as, let's say, bottom. Now, once I have a new layout with the name bottom, I can go ahead and open that. So for the bottom layer, instead of keeping it on the con layer, which is the top layer here, you can see, I can select both of these pads or multiple pads, whatever you have. In one shot, all of them can be transferred to con 2, which is my bottom layer. Similarly, this component body outline, instead of top, it will go to the body PT, which is on the bottom, right? Similarly, the solder mask information we have, which is solder mask, instead of solder mask top, it will go to solder mask PT. And similarly, here on the output side, instead of solder mask, we go to solder mask PT. So in virtually no time, I have component ready for the bottom side mounting. Now, once I have the component ready, the same capacitor could be placed either on the top layer or on the bottom layer. Currently, the view I have is only specifying its top side, mounting. So let me rename this view to layout underscore top. Now, once I have one layout view, I can add another layout view. So I can right click, new layout. And when I'm doing so, ADS will warn me saying there's already a layout view. Do you really want to create another layout? Yes, say yes. And now with the same cell, I have, so let me, make it a little smaller. Now you can see I have another layout view here. Now again, in this case, I will go and do customize P cell and now reference it to CHP 0201 underscore bottom. So that's the cell name, which is representing your bottom side, footprint. Click OK, save it, and we are done. Now, just to have absolutely clarity here, instead of layout, which is a default name, I'm going to call it view as layout bottom. Now let's place one more capacitor to our design. And in this capacitor here, let's make a connection on this pin of the QFP. Now, if I go and select this option, you can see these three are already placed in the layout, so they are not selected. Only new item is that one. Once I click capacitor, now it asks me, because ADS senses you have two views. Now it needs to know the right view to activate. So here, if I want to place the component on the bottom layer, I select bottom, click OK, and now I can place that here. Now, in case you needed to mirror this footprint originally when you are creating, you can use these mirror commands to easily mirror and then obtain the required, kind of footprint you need. All right, so once I have placed this component at the bottom, if I have to just do a simple routing, I can start from the con layer. This technique you already learned in the last two video. Click the period key, go down to the bottom layer, and then now you could simply make the connection as required. So now if I see my design into 3D, I can see all the 3D view of my component. You can see the component pad, the component body, the QFN, the via, and how the bottom side mount component is appearing. All right. So that gives you a good idea, and we finish one main topic of this tutorial. Other topics are not so time consuming, but it was very important to understand the footprint modeling. How do we do at the top? How do we do for the bottom mount? And I hope with this explanation you will find it easier to manage the footprint and creating these components. Now, the second topic I would like to talk about is library referencing. Now, using all the knowledge you gained till now, we could go ahead and create multiple footprints. I could create multiple components, and at the end of the day I will make an inventory in a workspace that can be used as a library for my board design or for my module design. So in the other case here, what I have done, thanks to my colleague Wenlei, she prepared this example where she has created these footprints for various sizes, as you can see here. And I also have various components like capacitors, few transistors, resistors, and all that. And using same logic, we also have a connector model here. So if you look at the connector footprint, and if I show you in 3D, it's like a typical plug-in connector. And I also have model for an SMA, and here is an SMA connector model, which is again very simple footprint to create with all the information you already have. Basically, these are same pad stacks, and you can create a separate pad stack for SMA connectors. And you can notice the pins you have placed on those, vias. Now also, because this is SMA for our board design, if you want to keep it at the input side, keep it at the output side, like we created multiple layouts before, for capacitors like you have here, you have layout, layout back, and so on. Similarly, even symbol can have two views, because if I'm placing the SMA connector on the right hand side or far side, I will have connectivity points coming to my left. So I want to use this symbol. However, if I'm placing SMA connector model at the input, then the connection will appear on the right hand side. So again, you can spread your thoughts and find out what you really want to do, and accordingly have more schematics, even more symbols, more layouts, whatever you wish. Now, using these two library models I have, so you can see I have a workspace here called component library underscore WRK. So it's like my central database, and it's just one time effort which somebody needs to put in and really create this. Now, you could pack all this information in a more sophisticated manner to create a PDK, and that PDK can be shared with the entire design team, and you can install it like how we installed the MMIC PDK or the Murata kind of component library PDK. But I'm going to probably have a video on that a little later, how to create your own PDK using some of these models here. Let's look at simple way of doing it. Let's say I can't create PDK, things like that. And you will also understand the key library referencing information while doing so. Now, once I have this workspace, I want to use this as my reference all the time. So just now I was working on a new workspace. So let's go ahead and create a new workspace. And let's say sample underscore understanding. All right. Now in this workspace, I don't want to create a layout technology because all my layout technology, whatever I need, is in my master, library, right? So I'm not going to create a layout technology. Just simply create this workspace. Now, once I have this workspace, I can go to Design Kits, Manage Library. Once I go to Manage Library, you can see an option here called Add Library. Once I click on Add Library, I can browse to that workspace where I have, created all the footprints. Like in this case, it's component library. Now inside workspace, remember we always have a library. So we just click on that folder and we select this folder. Now this library could be added as a read-only mode. If you add it as a read-only, the user who is using that can't modify any content of that library. You can't edit anything. If you open it on shared mode, the user will have authority to change anything, but that library can be only used by one person at a time. So while I am using it in some other workspace, nobody can open the same library and try to edit that library because it's in shared mode. But if you add it as non-shared mode, then I can use this library at the same time somebody else can keep on working in that library to either keep on adding newer components and things like that. And it's a live link. If I'm using the library and somebody creates 5 more footprints for me or 5 more components for me, all of them will be updated live here. Right. So in my case, I'm going to add it as a shared, just to show an example. Once I click on shared mode, ADS will warn you that it is in a different workspace and so on. We say okay. And now when you added it on a shared mode, you can see all this information will pop up into your current workspace. And if I go to library view, let me close this and let's go to library view. Now you can see you have 2 libraries. So this is currently your working library. This is where all your components are coming from, right? So this is what we call as library referencing. Now, if you don't want to confuse yourself because these components you don't want to see here under folder view, you may want to only see your own designs, right? You don't want to see library components here. Well, there's a way to do that. So let me remove this library from here for the time being, and you can see all the components are gone now. Now, when I go to add library and we go browse to the same location here. Now, instead of adding it in a shared mode, let's add it in a read-only mode. And once I do that, you can see the library got added in the list, but you no longer see any components here, which is like how regular PDK, kind of stuff comes in. If I go to library view, you can see there is no library shown here because now you added it as a read only, it will actually appear under read only libraries. And now you have all the components and all the technology and everything. It's just that you can't edit any of this design. And frankly speaking, I don't need to edit and in case it's not required. All right, so now if I create a new schematic here, I can use any component from that library which I have, just added, and I should be able to, pull in, required components for doing my circuit design. For example, here, if I need a sample capacitor, I can place a capacitor. If I need an inductor, I can place an inductor. If I need a transistor, I can place a transistor here. And if I need a connector, let's say this is for DC connectivity, I have a DC connector and if I need a NPN transistor or JFET, all of them are here basically, which you can use. If you okay, so similarly for SMA connector, you have a SMA model, and if you want to drag and drop, you can use a symbol mode, let's say for once, and next time you insert it, let's pick symbol alt, and now you have two different SMA connector, one for the input side and one for the output side, as you can place. So this is what we call as library referencing. Now, if we go back to the workspace we were working earlier, so we had these two topics in mind. So I have the footprint modeling, and I also talked about library referencing. Now let's go and talk about how can we do a quick RF board routing example. And just now I showed you a sample 3-component routing. We are going to use the similar kind of technique to do that routing. So in this case, let's go back to our screen here, and this is where I was talking about having a routing example. So here in the library which I added as read only, so I'm going to change that. So let's go to library, and here by right click I can change the library mode, and instead of read only mode, I'm going to change it to shared mode. Click OK, so that nobody else can edit while I'm using this. Not if anybody will do that, because I'm working on my isolated laptop. Now under folder view, I have an example here, which is like a 2-stage sample amplifier design. And this amplifier is basically having few FET components, few capacitors, few resistors, and this DC connector and 2 SMA. Now, if you have to do routing on this board, what you can notice, I have a layout here. Okay, so this is like a layout template, and I want to finish this design into this much of space. Now, using the technique which I just showed you for a sample 3-component placement, I could go ahead and put these windows side by side. And now I can activate that option, place components from a schematic to layout, and I can select this SMA connector. And again, you can decide your source and destination first. So let's place 2 SMA connectors. And now based on your logic, you can start using these components, start placing them as you need, and you can go ahead and do this routing very easily for yourself. So I will pause the video till I place all the components, and then I will come back to this video. Okay, so now as you can see, I have placed all the components, so no rocket science. I just placed the component in a logical order. And now you can also see the rubber band between those components. And now using all the knowledge, I'm sure you will be very comfortable, routing this. So here in this case, we can decide top, which is basically the top layer here, because I'm using my, colleague's example. And now using these connectivity, modes or the guiding lines, it's kind of very easy for us to go ahead and start routing the board as we require. Now notice here these 4 capacitors which you see in this case is on the back side or the bottom side. So when I'm routing from this point to this point is fine. But when I want to take my connection and to connect to this guy, I need to be on the bottom layer. And that's what we are going to do by using the auto VIA insertion like we talked about. And here now you have the connectivity to that trace, but here you can see it's kind of complaining because it's not connected properly. So it's saying I want to connect to that guy. So that's fine. We can insert a new trace from there. And once we reach to this point here, let me go to the bottom layer, and let's make a connection there. So now everything is kind of fine. Similarly, while going to this connector, I can go and route myself from the top layer. And from here, let's go ahead and join. So it's pretty simple. So this way, I will again pause the video and I will finish all the routing to show you the end result. All right, so by spending 2-3 minutes, I already routed the board, and then you can see it's not a very complicated board here. And again, I made this connection at the center point, and that's where it kind of accepted the connection, because if you're not at the center of the trace, the connectivity is not completed. And again, wherever I have to switch the layer, I have switched the layer, and then I have made all those connections as needed in the schematic. Now, once we have this design ready, basically we have our schematic design, and we also have the layout design. Now, this is a very simple case, but in real world, your case can be a lot more complicated. So one of the thing which we would like to do is to check our layout versus a schematic, just to ensure we haven't done anything wrong and we are not missing any of the components. Now, to run LVS in ADS, you have a native LVS integrated. So if you go to tools, you can see I have ADS desktop LVS. Now I'm going to use ADS desktop LVS. Once we click on that, you can define the rules or any specific rule you have to compare. But right now we just compare the whole design. And when we say run, now you can see everything is synced up. So there are 18 components in a schematic, 18 components in layout, and everything is kind of black, which means everything is working fine. If you have any error, it will be pointed as red. And once we click on that option, as you can see right now in this case, it is taking me, because the auto zoom is on, and zoomed into that location where you are looking at those components, which are basically inductors, and there are 4 inductors in here. So if I reduce this window here, you can see there are 4 inductors for which it is zooming in. Anyway, so there are other options. There are again advanced options here. If you want to do physical net connectivity, if you're dealing with IC or modules, if you're dealing with multi-technology module with a nested IC inside, I could do LVS check all through the hierarchy. And that's a beautiful feature of ADS LVS. If you're doing a module design, even with nested technology to handle multi-technology, I can traverse through the entire hierarchy and look at the LVS, piece by piece and at every, level of your hierarchy. All right, so that was a quick bit on LVS. And if you click on help, you will get a very detailed manual on how to use ADS LVS for all the conditions. LVS checking, we can also do DRC checking on the same design. So to activate DRC, we can go to tools, DRC. And in here, if you have a specific rule file given to you by your fab house in ADS format, you could go ahead and browse that, browse to that location and use a file. In case you don't have a file and you just want to do a quick DRC, you could create that rule file yourself. And if you are, knowing the AEL programming, you can also write your own DRC file. Now, if you just want to learn how to write a DRC tool file, there are plenty of information in the ADS documentation. But if you just want to create a quick rule file, you can click on create rule file, select where you want to store that file, and then you can define your, quick width and spacing rule, like what minimum width should be there, what minimum spacing should be there, which layer it should be applicable. And you can keep specifying those numbers here, and you can save. And once you do that, your rule name or rule file, whatever name you give here, will be saved at the location, which is specified by this file here. Anyway, so for this demo, I do have this example rule file here. And on this design, if I try to run DRC and make sure everything is okay or not. So one is the runs DRC, it shows I have 3 problems as per the DRC rule. And if I expand it, I can see the coordinate of where the problems are occurring. And if I switch on auto zoom and click on one of these errors, it will zoom into that location. And here you can see it is pointing out the distance between here and here must be greater than 8 mil, but you have less than 8 mil. So that's one error. Similarly, on the other side, it's the same via, but on the other side, you have the same issue, which is obviously, and so on. Now you can, switch off this DRC rule. And now if I just do this correction here, for example, if I just change the via little, away from that location, and if you try running the DRC again, and let's say run it again, And now you notice you only have one error because two errors were caused by this via, which I corrected. Now the another issue is about this via handling. It is saying this edge is at an angle which should be greater than 8, but it's not you know greater than 8. So now we can go ahead and we can click on this trace, and I can go ahead and edit this trace information, or I can reroute this trace. For example, I can make this trace to be routed something like this, for example, or I can just delete this trace and create a new trace. For example, sometime it is easy to kind of take out the trace. Press T command, and now from here I can go and route my connectivity like this. So my connectivity is still retained, everything is happening. And now if I just run DRC, and that hopefully there should not be any error now. As you can see, it's all cleaned up, everything is good, and you can do quick DRC here. Now, if we the last thing remaining, remember about the ground porting and doing the plane generation and putting stitching vias. So I have this layout here which is complete in all aspects. So if you look in a 3D, it's all completely routed two-layer board. There are few three components you can see, four capacitors at the bottom, rest of the components on the top side with two SMA connector pads and everything. Now, just before releasing it to Fab, if I want to run DRC, sure, we can go ahead and run DRC on this design. And now you can see it finished in like 2 seconds, checked 640 shapes. There's no error in my design, giving me the confidence to go ahead and launch this design for fabrication. Right, so that's all for this video. Hope you like the learning I provided in this video, and all these three videos put together will give you all the required information to be successful with multi-layer designs using ADS software. Thanks a lot for staying till the end and watching all the tutorials I'm posting on my YouTube channel. Best of luck designing your multi-layer circuits with ADS.